I'm Kilian, and I'll tell you today a bit about DAG-like lift. So somehow as a motivation, so what have we seen so far? We have seen we have seen monotone interpolation. So how does this work? Well, we have like monotone circuits, right? And if we have a lower bound for this, then we can somehow transfer this into a resolution lower bound. And this is like the feasible interpolation, or that is just like interpolation. Okay. And then we've also seen that if you actually have monotone real circuits, so if you have monotone real circuit lower bounds, then we can transfer this somehow to cutting planes lower bounds. And this was somehow done by Goodluck, and then later on by Goodluck, the FPPR paper by blaming Goodluck, and no, not Goodluck, blaming Pitassi, Kretov, I think, and Robert, and then we saw the proof by Sokolov, who like somehow touched these lines. All right, and so today we want to talk about the reverse, in the sense that if we take something that is resolution width hard, then we will show how to get monotone circuit lower bounds. Okay, and this is not immediate. Like if we have something that is hard for resolution, then we need to compose it with a gadget, and then we actually get the monotone circuit. All right, so this is somehow the plan, and just like the informal theorem that we will want to prove today, or at least parts of it, we'll cover the details of the proof on Friday, is that if CNF phi is width hard or resolution, then this implies that related function f is monotone circuit. Let's just say monotone. Okay. And if I'm a bit more detailed, so if the CNF is really like omega n hard for resolution, then we will get a circuit lower bound of the form 2 to that to the upside. But we'll cover this in more detail. This is just some other output where we want to go. We can also show with similar methods, we can also show that if something is width hard for resolution, then it is actually cutting planes hard, or respectively monotone real circuit hard. But I don't think we'll have time to cover this proof also. It will build on what we proved today, or today and Friday, and uses very similar ideas, but you need to work a bit harder. I don't think we have the time to cover all this, but we'll see how far we get. All right, very good. So I'll first cover. So in the first hour today, we'll cover some background, just so I'm sure that we're all on the same page, and then we'll show actually this theorem. So we'll show a monotone circuit lower bound, and then in the second hour, I'll give a high-level proof overview of this theorem. Okay, very good. So we'll talk about search problems today, and in fact, total search problems. So how are they defined? We have some input domain and some output domain, and so a search problem is a subset on this thing. And it's total in a sense that for all inputs I in I, we assume that there exists some output O, so that I O is in S. Okay, so these are total search problems. And we'll be interested in 2 of these total search problems. One will be the falsify clause search problem, and the other one will be the monotone Kashmir-Victor solution. Okay, let me just quickly define these. So we fix CNF F, and the falsify clause search problem So falsify clause search problem defined as follows. So as input, we get an assignment in 0, 1 to the n. So we get an n variant with assignment, final, whatever. We assume that this is over n variables. And so as an input, we get an assignment, the variable is base formula n, and we're supposed to output a falsified clause. So output is a falsified clause of n. Clause C n, so that if we get an assignment of row, then C of row is equal to false. Okay. So this is our first search problem that is associated with the CNF, and it's total if our CNF is really is unsatisfiable, doesn't have satisfying.
We have a request from video, slightly larger font.
Larger. You can try. All right. And then the other problem we're interested in is the monotone Kashmir-Vickerson game. So for this, we fix a monotone function. The monotone function f mapping from 0, 1 to the n to 0, 1. And is it clear what monotone means? So, right, so what is monotone function? A monotone function satisfies that f of x is less than f of y. If for all I in n, we have that xi is less than yi. Okay, so that is clear. So, like, yeah, you can think of these functions as if you look at the Boolean cube, then we have some ones up here, right? And we have zeros here. Well, they're nicely altered. Always going from 0 to 1 on any path. The old 0 string, here's the 0 string into the old 1 string. Okay. So we have the monotone function, and for monotone Kashmir-Vickerson, we're given an input from the one input and the 0 input, and we're supposed to find a bit where they differ, where one is less than the other. Okay, so input, and we're given an alpha in from the 1 inputs and the data from the 0 inputs. And we are supposed to output an index I in n, like an index, so that alpha I, which should be 1, is strictly larger than beta I, which should be 0. Okay, and because we're monotones, that's such an imperfect. Okay, very good. You can also play this game of non-monotone functions. That's just a Kashmir-Vickerson game, and that actually characterizes the depth of a circuit required to compute anything. Okay. Very good. Okay, and then we will also need to talk. So sorry, I'll denote this by monotone Kashmir-Vickerson, and the falsified clusters problem just by S. Okay, and this will be monotone Kashmir-Vickerson. So all right, and then I need to introduce again the DAGs, these abstract DAGs. I have introduced them already in the lecture on cutting planes lower bound for random CNFs. And as such, I hope this is a review. But if there are questions, please interrupt me. I will cover it fairly quickly. So what is such an abstract DAG? We're given a directed acyclic graph, right? And with a single root node here, this root node has in degree 0. Every node in our DAG has out degree 2. And every every node is associated with some function f. Let's call this the root, so this is the f of r. But if you look at any node in this DAG, when it has out degree 2, might have large integrity, and this vertex u will be associated with some function f sub u, and we have like here children v and prime. Okay. So an f DAG is such a directed acyclic graph with the following properties. So for all vertices u in the DAG, they satisfy that f sub u is from this family of Boolean functions. And all these functions here, these little f's, are from the input domain to 0, 1. Okay. And then we have the condition at the root. We want that, so basically we want this to be a refutation. So we should think of whatever you map to 1 at a single node, this is what assignments you rule out at this node. And we clearly want that at the root or at contradiction, if we think of it as a proof, we want that all the assignments are ruled out. So this is the condition at the root. So at the root, we want that f sub r is satisfied that this is just a constant 1 function. Okay. And then for any node u, not a leaf. So I'm writing this small. So for every u, not a leaf, we want the following property. We want that somehow this proof system is sound. What this means is that whatever v and v prime rule out, then whatever u rules out has to be contained in what these two nodes rule out. Okay. So what this means is that if we have this u, f sub u here, and we look at what is mapped to 1, so the inverse of what is ruled out, right? All the assignments that are ruled out by this function has to be contained in the union of the same thing from children. Okay. So the f inverse sub v of 1 union f inverse sub v prime of 1. Okay. And this is kind of saying that if you're at any point in your proof, right, then we should think of it as a bottom up. We're ruling out some assignments, we're ruling out some other assignments, then we can write down any conclusion from this holographic f set here, which is implied by these two things. And what does implication mean? This means just that whatever this node now rules out has to be contained in what the previous two nodes rule out. Okay. So this is the condition at the leaf and non-leaf. And if we have a u, which is a leaf, then we want it to actually solve our search problem. Okay, so we have an f DAG solving a search problem S, solving a search problem S. We want that at the leaf, we actually point to a solution. And we want that whatever you rule out at the leaf is actually contained in a solution. Like it's a valid solution for anything that is ruled out. Let me write this. So what I want. So for a leaf, we have that U is labeled by some output O, right? Such that whatever we rule out at this node, fu inverse of 1 is actually such that for all alpha that are ruled out, right? For all assignments that are ruled out, we have that alpha O is in the search problem. Okay. Does it make sense? So then we're saying that this f DAG actually solves our search problem.
So this big F is just the set of all the FUs, that's it?
Yeah, no, you should think of it as a larger set
of
base functions that you're free to use.
Yeah.
It might contain more than just this. What is used?
Okay.
It's just a subset of the powers.
Yeah.
Oh, okay.
Yeah, like you can think of it as everything, but then it's a very powerful proof system. So you want to somehow balance it so that you don't choose too many, so that your thingies are weak enough so that we can prove the results.
Okay.
Okay. All right. Very good. Okay, I'll make it more concrete instead. All right. Let me see the anything. Okay, very good. So now let us consider our input domain to be bipartite. So it's like some x times 1. You should really think of this as the communication setting, where at least we get part from x and something from x, and both will get something from y. Okay. And now we can look at all combinatorial rectangles. Okay. So let us say that you get a neat name. So we can set F, this calligraphic F set, to be all the sets U times V, for U a subset of X and V a subset of Y. Okay. And now, so this is one example. So this is very concretely, these are the so-called rectangle tags. Okay. So for a search problem S, I can now define the rectangle DAG complexity of a search problem S to just be the minimum sized rectangle DAG. Let's call it rectangle DAG solving S. Okay. I mean, yeah, I guess I'm calling this rectangle. Okay. These are our rectangle DAGs, and this is a very interesting complexity measure in a sense that we can prove that the rectangle DAG complexity of a search problem is the monotone circuit complexity of the Boolean function f is equal to the rectangle DAG complexity of the search word, like monotone Karchner-Wiglerson of f problem. Okay. So the monotone circuit complexity of any monotone Boolean function f is equal to the size or equal to the rectangle DAG complexity of the monotone Karchner-Wiglerson search problem of this monotone Boolean function.
Rectangle DAG related to communication. How is rectangle DAG related to communication complexity 3?
It's not.
It's not.
No. It's a DAG, right?
Yeah.
I mean,
you're
usually interested in the depth of these protocols if you're in the normal setting. And there it doesn't matter whether you have a tree or a DAG.
Yeah.
Right. But somehow we're interested in the actual size of these DAGs now. And then it really matters whether you have a DAG or a tree.
I don't know if you mentioned, but like if it's a tree rather than a DAG, then it's just a communication.
Yeah.
Okay,
That's
fair.
what I was asking. Yeah.
Oh, sorry.
Yeah.
Sorry. Yes.
Okay.
Very good. Yeah. My bad. Yes.
But like, yeah, it's a point worth making, right? That standard tree-like protocols, standard communication protocols would correspond to tree-like proofs. The whole point is that we're not interested in tree-like proof systems because they're usually easy to prove lower bounds for. We want general proofs which can be DAG-like, and now also we're sort of changing the communication model to work with DAGs, whatever that means.
Yes.
Okay, whatever that means. Well, what Kilian wrote on the board.
Yeah, and if anyone knows DFNP, this can also be viewed as a PLS communication. Yeah. If you don't know these words, just it is. All right. So why is this rectangle DAG actually an interesting communication? Not communication. Why is this an interesting complexity measure? Okay. So we can, for example, look at all functions f. So let us look at all functions f sub c, which can be computed by deterministic tree-like communication protocol. Okay. This is a very powerful class. So Fc is now the family of functions. Computed by a tree-like communication protocol. What's that? C, right? That C, which we can think of some polynomial. Okay. The red polylog is usually considered like efficient, so we can look at all functions that can be efficiently computed by a tree-like communication protocol. This is a large function or large family of these functions, which certainly contain these rectangles, right? And this, if you have a FC DAG now, this can clearly simulate resolution or I mean, this can already simulate resolution, but also cutting planes of bounded coefficients. Okay? And the cool thing is that we can simulate an FC protocol by a rectangle DAG by only a 2 to the C blowup, right? Because we can like replace every, yeah, basically we can just bake this communication protocol that you compute at every line just into the DAG. Okay, so you can like take your DAG, which is an FC DAG, and then you can transform this into a rectangle DAG by just looking at every node here. This will be labeled by some F, which is computed by some tree-like protocol, and then you can just bake this tree-like protocol into this DAG. And so with at most a blow up of like 2 to the C, we can actually, if we lower bound rectangle DAG, we also lower bound this proof system. Okay, and this is like a quasi-polynomial factor, which is small as long as we prove like exponential lower bounds for the rectangle DAG. Okay, so this is somehow a good system to study, right? It's like fairly powerful and will give us nice. All right, very good. So I haven't told you yet what resolution is in this system, or like in these DAGs. And these are just the so-called conjunction DAGs. Let's quickly write this down. Right, then we can look at the conjunction DAGs. Which is also known as a resolution. For now, our input domain is just 0, 1 to the n. And we take any conjunction as our f, right? So now our f, our family of function, is just any conjunction of literals of a subset of literals. Does this make sense? I don't want to formally define this any further unless it's unclear. So a conjunction is just an AND of some literals over the n variables. And this just corresponds to resolution. And then again, we have the conjunction complexity, conjunction DAG complexity of a search problem, which is defined analogous to the rectangle DAG complexity. And we have the width of a search problem, which is just defined to be the minimum over all possible highs or possible conjunction DAGs of the maximum width of any clause occurring. So C I shouldn't say conjunction. C is now conjunction, and just the width of any conjunction. Just the normal width of we have seen in resolution. Okay? Hope that's clear. Good. Now, okay, so, okay, very good. So I told you many definitions, and yeah, so what can we say? So let us fix a search problem, fix any search problem S.
And Kilian, just to ask, I mean, we're actually saying that conjunction DAGs are exactly a resolution.
Yes.
Right? Which would require an argument, but it is true.
Yeah. It's just you flip the proof upside down. That's literally the proof. And then, yes. Yeah, very good. This is, okay, fine. I'm claiming this is equal to resolution. And it requires some staring at it to see. Yes. Okay. All right, but now we can fix any search problem S, and right, we said that S is like some subset of input times an output, and we can split I arbitrarily into two sets, X plus Y, and then say that now we get an equivalent search problem S prime over X, Y, O. Okay, so we split I into two parts, but we need to do this to be able to talk about rectangle DAGs, because conjunction DAG doesn't have a bipartition of its variables. So I want to enforce this, and then I'm claiming that the rectangle DAG complexity of S prime is a lower bound on the conjunction DAG complexity, of S, which is bounded by n to the, let's say, order of width of S. Okay, so this one is just a trivial upper bound of any resolution proof on in width W is of size at most enter W, because there are no more clauses than that, right? And here I'm just saying that if anything is conjunction, then it's also a rectangle over the bipartition. So this chain of inequalities. And what we will show today is that if we take a search problem over on the left-hand side and we compose it with a gadget, with the indexing gadget, then this will actually attain the maximum size that it could ever have, namely n to the width of S. Okay, this is like our main theorem. Okay. All right.
So the partition can be completely arbitrary, like any partition gives us an S prime that satisfies this bound.
So all you need to observe is that if you take any conjunction and you split your input domain into two parts, then this will correspond to a rectangle.
So you're saying on the far left, you're implicitly maximizing overall bipartitions.
Yes, if you want to, yes. But yeah, so for any, yeah, yes, you can, yes. What are you saying? Okay. Is it clear? All right. So what is that? So, okay, I need to recall the indexing gadget. So we have the indexing gadget sub n of mapping n times 0, 1 to the n to 0, 1. How does this work? Well, we should think of this n here as an index into this large bit string. So what do we have here? We have a little integer from 1 up to n. And then here we have this huge bit array, right, of length n. So looks something like this, right? Maybe 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1. Here maybe we have 4, right? And then we point to, this means it points to the fourth index in this long bit string, and the output should be this thing. So in particular, if we have index of m of x, y, then we want this to be y sub x. Okay. Very good. And I need to tell you what it means to actually compose a search problem with the indexing gadget. So if we have a search problem S composed with the indexing gadget, what I mean by this is that before our S here had an input domain of 0, 1 to the n times the output. Okay. And now what we'll do is this indexing gadget is now defined over n times 0, 1 to the n times, right? Because I have n copies of it. And each one of these copies will replace one of these original variables. Okay. So what does this mean? So this composed version will map from n to the n times 0, 1 to the n to the n to the output. Okay. And so given given an x, y in this input domain, right? This is in here. Then we want to find an output O such that ZO is in S, right? So where Z is now the string computed by indexing on this XY thingy. So what am I saying? So Z, where Z is equal to indexing to the ends of M of XY, which is just equal to the concatenation of these things, right? So we have X1, indexing sub M of X1, Y1, and so on, up to indexing of Xn, Yn, I guess. Does this make sense? So we let indexing compute, like, right? Yeah, so XY is like in this domain, and like for each part, we'll compute indexing separately, and it will compute one coordinate.
And just as a sanity check, this is exactly what you saw before, except we called it lift then. This was the lift M of S, but this notation is probably slightly more common. So it's like exactly the same thing.
One. Yeah. Okay. Yes. Good. Very good. And so now I can say our main theorem, which is that if we compose S with indexing, then the rectangle DAG complexity of this composed version will be equal to n to the width of S, okay? Which is like the maximum there. All right. So theorem. So for n, some large n to the, I don't know, 1,000 or so, large constant, not entirely sure what it is, it holds that the rectangle DAG complexity of any such problem S composed with indexing with over n bits, right? This is equal to n to the theta of the width of S. Okay, this is the main theorem we want to prove, or at least give a high level.
Whose theorem is it?
Thank you.
Is it like mine?
No, it's not mine. It's GGKS. I think it's from 17, so this is Göös.
Garg, Göös, Kamath, and
Garg.
Sokolov.
No, it's Garg, Göös, Kamath, and Sokolov. Yes. Very good. Thank you.
Are you going to show the original proof?
Huh? You sound skeptical. Sound like you know more than I do.
It's just disappointing.
Right. All right. So good. So what does this give us? So this tells us that if we take anything that is resolution hard, then certainly and we lifted with the indexing gadget, then it's also resolution hard. Okay. But even more, because we saw that this rectangle DAG thingy captures this proof system defined over any efficiently computable functions like communication complexity by a small communication protocol, we get lower bounds, like essentially optimal lower bounds for all these kind of proof systems. Okay. So in particular, this includes cutting planes with bounded coefficients, but it does not include cutting planes with unbounded coefficients. Okay. And if you would want to do this, then you would have to replace this rectangle here by triangle. And these authors also proved the same theorem for triangle DAG complexity, where a triangle we saw before is like a rectangle, but it looks like a triangle. It's very helpful, you know. So whereas we can have a rectangle looking something like this, a triangle is just there is an ordering of the rows, say, of the columns, so that they are like monotone decreasing as we go to the right. Okay, so this is a triangle. So a triangle, then we make this happen. But note that the triangle can also look something like this, or maybe something like this. All right, but the proof of the triangle DAG lower bound is basically the same as rectangle DAG. You just need to work harder. Not trivial amount, but it's doable.
It's clear that the composing, the indexing also works when you move to the function world. Like you have a lower bound on rectangle DAG of S composed with indexing, and now you want S to be monotone Karchmer-Wigderson of F.
Just give me 10 seconds.
Okay.
Yeah, you basically, so, okay. What Noel is asking is how do we go from a composed search problem to a monotone Boolean function and actually to play the Karchmer-Wigderson game there. We will show this in the remaining, I don't know, 15 minutes or so. Okay, and then we'll figure it out.
Okay.
So in particular, this theorem, yeah, so, okay, any questions about proof complexity applications? Is there anything unclear? So yeah, what you should remember is if you have something that is resolution width hard, then it's hard for cutting planes and any like proof system that whose lines you can compute with an efficient communication. Okay.
I mean, maybe it's worth two things is that you said that this is F setup is very, very general. So you can now start to look at different kinds of F families, and this will give you different proof systems. And this is super important to try to extend this to, for instance, getting this for resolution with parities would be fantastic. Another thing you could say also, you just wrote m equals n to the 1000. We actually care about the exponent.
Yeah, you're going to the open problems.
But I'm getting to the open
lecture. Okay, fine. So I'll tell you already about this. So major open problems because Jakob forced me to. Yes.
So it also might be worth mentioning that this is a semantic proof system, which is really annoying.
Okay, fine. Yeah. So okay. So one downside of this proof is that it holds for the semantic version, whereas we would like to have arguments that only work for the syntactic version of these proof systems, but we don't know how.
Yeah, it's cute. If you can represent DNFs in your proof system, you can prove any proof system that can represent DNFs as lines can prove everything in like one in
semantic version.
Yeah.
Yes. Semantic.
So you're screwed.
Yes. Very good.
Except for resolution, we actually do have the base thing we started with is proper resolution.
Yeah. Well, no, it's also semantic resolution.
Yeah, but it happens to be the same.
Oh, really? I never thought about such. Nice.
Maybe we should put it on the problems.
Yeah, it doesn't sound too difficult. Not that it's safe. Okay. So all right. So let me mention some open problems. So clearly, this n to the 1000 is annoying. I believe it has been improved now to n squared plus epsilon. And you would know best, I guess.
Well, that's a weird thing with some power.
Yes, this is correct, right? Okay, good. So this has been improved to a small polynomial, now a handleable or understandable polynomial. Getting this to constant would be amazing. I'll tell you why in a second. But just getting it to polylog would be already a huge breakthrough, I guess. And then another thing.
It will be possible?
Yes, what?
Do you hope that it will be possible to?
You shouldn't ask me. I don't know. No, I haven't told you. I don't know much about this.
Oh, okay.
So I think people. Yeah, no. Intuitively, it should be fine. Also, yeah, I believe it should be fine for constant, and I think this is also the consensus, as I understand, or that people hope that it's. But yeah, just don't know. And so. Yeah, then you could ask for other objects here. So instead of triangles, you could look for intersection of triangles, which would be thus resident lower bounds. So disjunction of parodies, lower bounds, as well as something else. Resolution over cutting planes. So not stabbing planes, but the DAG-like version of stabbing planes. So, yeah, anything else? Yeah,
So we can say that resolution over cutting plane is basically now you have clauses, right? But instead of literals, you have like linear inequalities. You have disjunctions over linear inequalities. And now you can sort of, I guess what you can do is you can either resolve always, but you can also sort of unpack and sort of work on the linear inequalities inside the disjunctions by cutting planes. This is not a super proper definition, but this is basically resolution over cutting planes. You can define resolution over blah, where you have disjunction of blahs, and then you let the blah system operate on the literals, or you do resolution over clauses. And resolution over CP is like ridiculously powerful.
I think it's contained standard trig.
Okay. I would say extended trig is also would qualify as ridiculously powerful.
I would agree, yeah.
It's 1 plus epsilon and
1 plus epsilon. Oh, well. Thank you. So, fast and linear. Yes.
So how is this connected to monotone circuits? Like, do you?
Yeah, I'll get there.
Okay.
The next thing will be one.
Okay.
Okay. So, I'll have to erase this theorem, but remember the monotone circuit complexity of the function f is equal to the rectangle DAG of the monotone partial recursive complex. Okay. Keep this in mind. Right. So, a follow-up work to this work. So this is a corollary, I guess. This is due to GKRS. So they lost the first author here. So it's now just Göös, Kamath, Robert, and Sokolov, not just those guys. And they show that 3XOR stat, I'll define it in a second. Just this is a function that is computable in NC2, so it's very low complexity in the non-monotone world. But at the same time, you can show that this function requires exponential size in the monotone world. Requires monotone circuits of size 2 to the n to the epsilon. Okay. Good enough? So what is this showing? This is showing that there exists a function that in the non-monotone world is super easy to compute, namely in NC2, so in log square depth with gates of valuing 2, right? So super easy to compute, but in the monotone world, you require super large size. Okay. So what is this function here defined as? So the input to this problem is a 3XOR instance, and we'll encode it in a naive way that it's just a function 0, 1 to the capital N. Okay. And this capital N is equal to 2n cubed, which is just equal to how many XOR constraints you have over a set of n variables. Okay. And every bit indicates whether this XOR constraint is present or not. Okay. In fact, this is an upper bound. And then we output whether this system is unsatisfied. So we output 1 if and only if the encoding of this 3XOR instance is unsatisfied. Okay. So this is our domain, and we have 3XOR sat of some instance I, right, is 1 if and only if I is upside. There exists no assignment that satisfies this encoding of the instance. Okay. Is the definition clear? So we're given as input a 3XOR instance, and we're supposed to tell whether it's unsatisfiable or satisfiable. And every bit of the input tells you whether a 3XOR constraint is present or not. Right? Any constraint here is just of the form like xi, XOR xj, XOR xk is equal to some bit b, I don't know, yeah, b. Right, so we have n choose 3 choices or n cube choices at most for the side, and then 2 choices. Right. Okay, so how can we prove this? Well, we want to use this theorem, but in order to do this, we need to somehow relate this 3XOR stat to a composed search problem. Okay, and it will be the Zetin formula composed with indexing. What is the idea? Is to argue that the search problem, the closed search problem of the Zetin formula composed with an indexing gadget reduces to monotone Karshner-Wigderson game on this 3 XOR set. Yeah, and before we go down further this road, there's another reduction for how to get from a search problem to a monotone function due to Raspberry. But I will not cover it. I'll just cover this one because it's just sort of. All right. So let us fix Zetin formula F. So fix Zetin formula F. And let us say we have how many constraints? We have T constraints. So we have with constraints C1 up to CT.
Telling us anything about the width of the Zetin formula? Or, I mean, the degree of the underlying graph, or we don't care? I guess.
No, the underlying graph has to be of degree 3, right? Because, yeah.
Thanks.
Ah,
Degree 3 graph, Zetin formula, good.
Yeah. You were like one step ahead of me. Each constraint here is of the form like over Z variables, so it's like Zi XOR Zj XOR Zk equals to some bit. So the underlying graph is of degree. Okay, very good. And we're over variables C. So over variables Z1 up to Z, I guess, N. Okay. And we want the reduction from the composed search version for Zetin to the monotone Karshner-Wigderson game of 3 XOR. Okay. So how will this work? Well, Alice will get a string x1 up to xn in n to the n, right, on this side. And she will define an XOR instance, and also independently Bob will define an XOR instance. And we'll just argue that, well, whatever they will output from these XOR instances will just be a solution for this monotone Karshner-Wigderson game of 3 XOR. Okay, so I'll just define 2 XOR instances, and then we'll see what's happening. Okay. So Alice gets as an input this X string, and then we define 3 XOR instance. Over variables B, I, J for I in N and J in M. Okay, so this is our set of variables, and the 3 XOR instances that Alice will produce will be the same as F, except that it will be over different set of variables. Okay, so same formula as F, same formula as F, but over variables. Now the choice of variables will depend on her input. So it will be defined over variables V, I, X sub I. Let's just write it out. V1, X1 up to Vn, Xn. Okay, so we take the same formula as that, but instead of over the variables Z1 through Cn, it will be over variables V1, X1 up to Vn, Xn. Okay, where you should think of as like, right, so you can think of these VIJs as living in a grid, and you're somehow picking one variable per column, depending on this xi. Okay. All right. Very good. And then I need to tell you how Bob creates his XOR instance. And what Bob will do is that he will choose, he will get a string y as an input, and he will view y as somehow a planted solution to his 3 XOR instance. Okay? So what Bob will do, so Bob will get y in 0, 1 to the n raised to the n. I feel like everyone's still stuck over there. Does it make sense? Or so we take the same formula f, but it's over different variables, and the choice of the variables is dictated by the input to Alice. Okay.
And xi is an m array variable.
Yeah. Okay. Okay. Yeah. It's like an integer between 1 and n.
I mean, in terms of the lifted CNF formula that we saw in the last 2 lectures, this is just taking Alice's variables and actually hitting the formula with Alice's selector variable. So just as you're saying, Kilian, you just get out exactly a copy of the stating formula you started with. The only thing that has happened is that the variables have been renamed.
Yes. Okay, so Bob will construct a variable, a formula constructs a formula over the same variables, as Alice has. But now we view y as a planted solution, and we add any 3 XOR constraint that is consistent with y. Okay? So construct a formula over the same variables, views y as a planted distribution, right? This is the input to Bob as a planted solution. And then we add any constraint, any 3 XOR constraint consistent with y.
So why should falsify the formula?
No. Y satisfies the problem. Okay. Which will be a 0 input to 3 XOR SAT, right? Because we output, so Alice formula that she constructed will be a 1 input to 3 XOR SAT, right? Because it's unsatisfiable, because we assume, well, I guess I didn't say this, but we assume that the stating formula we start with is unsatisfiable. Okay. On the other hand, Bob's formula that we created has a solution, namely y. So it's a 0 input to the 3 XOR SAT instance. Parsable?
So just to see if I understand, so basically you're saying, again, Bob is just taking the y string and he views it as an assignment for v11 up to vnm. Okay. And then he just goes over all ternary XOR constraints. The whole 2 to the n, choose 3, capital N, choose 3 of them, or whatever the number is. And then he just checks, like, for every ternary constraint that is satisfied, he just says, oh, this is in my input. And now he gets like a super dense instance, but by construction, this particular bit string y will satisfy it, because those are exactly the ternary parity constraints that I include. Exactly. So Alice will have a very sparse instance that is violated, that is unsatisfiable, but Bob will have a very dense instance that is nevertheless has a planted solution.
Exactly.
That's the game.
Very good. Yes. All right. And now I'm just claiming that the monotone Carson-Wigderson game on these 2 inputs. So, and the monotone Carson-Wigderson game on 3 XOR SAT will actually output a valid solution. So all that remains is to argue that any solution to the monotone Karshmer-Wigderson game on this 3 XOR set problem, right? On these inputs that Alice and Bob created independently, gives a solution to, I guess, the search version of Zeytin, or let's just call it S sub F, composed with index. Okay. Okay, it's going to be very quick, very quick. What are we going to do? Well, we're going to get a constraint pointed out that is present in Alice formula, but not in Bob's. Okay, what does this mean? Right. So any solution points out a constraint C present in Alice, but not in Bob. In A, but not B. Okay. This clearly means that under the assignment Y, this constraint is falsified. Okay. So clearly, the constraint C of Y has to be false. 0. Okay. But at the same time, this constraint is over these variables here, right? So clearly, it's also falsified by indexing on X and Y, right? So we're done. Right? Good.
You should be more precise. You mean at all 3 XOR constraints, not at the right for the Bob constraint. For the Bob input, you're adding every 3 XOR constraint.
Yes.
Yes. Just
At any yes. Yeah. Sorry, my bad. Yes. Every. Yes. Very good. Thank you.
I think these are synonyms in this.
yeah.
Yeah.
So
But
like
any
not
is dangerous to
literally.
use. I understand. Yeah, I understand. Every 3x. So what have we shown? Come on, we have shown a monotone circular. It's pretty cool. And now, if you would want to get optimal 2 to the n lower bounds, you would have to actually reduce the size of the gadget deposit. So, good. That's all I want to do in the first hour. It was a bit longer than I wanted. But let's take a break for 10 minutes.
And I guess, is it true that, like, I really don't know the monotone circuit complexity literature, but they're chasing like truly exponential lower bounds, like exponential in big omega of n, and now we're getting tantalizingly close because now we have like exponential in n minus epsilon in this thing, right? Because the lift length is n plus epsilon, so you're going to take that hit.
Yeah, I don't know how the parameters split together.
Or something, or do you lose more somewhere?
I don't know.
Maybe.
Not obvious.
Anyway, but it's like it's exponential in n to the delta for some fairly large delta, but you would like to push delta all the way to 1, and in order to do that, you want to improve the lift length.
Yes, you want this. Good. Let's take a 10-minute break, and then we'll come back and look at the proofs this year. Yeah. Let's look at the proof of this theorem. So what do we want to prove? We want to prove that if you're given a rectangle DAG of size n to the d, then you can somehow extract a resolution proof of width d for s, okay, or contraction DAG, whatever you want. Okay. So what do we want to do? So we're given a rectangle DAG I of size n to the d. And we want to construct we want to construct a resolution proof. Let me just call it resolution proof of width d. Okay. To me, this seems like a very strange problem because, right, we're given a proof somehow of some size and we somehow want to extract a proof of low width. To me, I didn't know how to approach this before I read this paper. Okay, but certainly what we need to look at is somehow we have the unlifted side S, right, where we want to solve the search problem S. And on the other side, we have this composed problem. So S composed with indexing. And so we somehow need to relate objects from this side with objects from this side, right? Because ultimately we start with like somehow these rectangles in this domain and somehow want to translate them into disjunctions, or sorry, conjunctions of low width. Okay, so what does this look like, right? On this side, we're over these split variables. So we have X and Y, and we have some rectangle. And over here, we are somehow working over the Boolean cube. This seems to be like the what to look at. And what I would like to say is that for any large rectangle on the right side, we can somehow associate it with a subcube with low codimension, right? Because the subcube of low codimension really corresponds to a clause of low width. Okay. So what do we want to say? We want to say that if we have a large rectangle here, then we can somehow transform this into a subcube of codimension at most B. Okay. All right. For example, the first thing we want to do, I'll specify later about how we do this, like in more detail. And so then the high level idea will be, well, we're given this proof pi, this rectangle DAG, right? And what we'll do is we'll somehow walk down this proof and we'll like construct a defendant or prosecutor strategy, right? Like we have a prosecutor defendant game that characterizes resolution. So we just want to create a prosecution strategy in low width. Okay, that's all we need to do. And if we can do this, then we're good. Very good. And so now what you want to do is that at any point here, we'll be looking at something like this, right? Where we have a rectangle. And what we want to maintain while walking down this proof is we want to maintain some structured subrectangle. Okay? And this structured subrectangle that we will maintain throughout walking down this DAG will have the property that it is actually a subcube on this other side. Okay? So that we can then really like extract a resolution. This is the very high level, very sketchy argument of what we will want to do. It's highly not obvious how we do this or how you actually get to this. But I hope like at least the high level idea makes sense. So then in order to implement this proof plan, I need to tell you somehow what does it mean to be structured for this thing. This is like the key invariant that we'll maintain throughout walking down this proof. Okay. And so if you know lifting, then this is literally just called the row structure or like row-like in the end. But this is what I'll tell you now, what this precisely is. And then once we have these definitions, I'll give you the proof, the high-level proof, assuming like some lifting lemma. And then on Friday, we'll do those lemmas. That's at least my plan. All right. Okay, so we'll always switch between these two sides, the composed side and the non-composed side. It's sometimes difficult to keep track, so if you get lost on what side we're currently at, please interrupt me and ask. Okay, it took me a few times to get the sides there. All right, so what do we have? So we have some rectangle on the composed side. Okay, so this means it's somehow living as a subset of n to the n times 0, 1 to the n to the n. Okay, so we have a rectangle. And we're going to say this is row-like if this thing here happens. Okay, so we're going to say that R is row-like, where row is really a partial assignment. So This is a partial assignment. On the unlifted variables, so on the left side, unlifted. So if the image of R under the gadget, so I'll just write G as this indexing M sub n, okay? So under G, so if you look at the image of R under G, if that corresponds to the conjunction that is satisfied by rho, okay? So what am I saying? Under G is the subcube consistent with rho. Or in symbols, I'm saying that R is rho-like if and only if, and if you look at the image of R under G, then this is equal to the if we can look at the conjunction defined by rho, right? There is a unique conjunction satisfied by the partial assignment of rho, a unique maximal, I guess. And then look at everything that is satisfied by this. So look at all assignments that are consistent with rho. Okay. I want to say that R under G, so I take R, which lives on the composed side, I put it through G, I'll get a bunch of assignments to the unlifted formula. And I want these assignments to be exactly the assignments that are consistent with rho. Okay? And this will literally say that if R is rho-like, then we exactly have this link, right? If I have a rectangle R that is rho-like, then it just corresponds to a subcube on the unlifted side, right? All right. And just like to like maybe illustrate this once more. So what is happening when we pass it through G, right? Like we basically have this long string and then like some, right? We take an assignment on this side, we put it through G. This will like point out something here, like maybe 1 or 0. And like all these assignments need to be consistent with rho. Okay. All right. Yeah, but also note that somehow passing from here to here, there might be a lot of collisions in the assignments, right? Like I can have two assignments that maybe point to something else, but they both times output 1 for the same variable, right? So this is a very lossy step happening. All right. So instead of actually just maintaining that this rectangle R is rho-like, which is probably very hard in such a thing, we're going to maintain some other properties that are a bit nicer, which are basically saying, well, on the X side, we'll have a very nice distribution, which is almost uniform. And on the Y side, we'll just have many of those strings. And if this is kind of satisfied, then it should be clear that in this step, we're not losing anything. So in particular, if we can satisfy that X is a very well distributed in R, and the Y assignments are basically everything or almost everything, then we should still be able to find all these assignments and then show that this is rho. Okay, so we'll weaken somehow our requirement, seemingly, but then show that this implies rho. And this is actually then something that we can maintain throughout this proof structure. All right. Very good. Well, let me actually give you so we want to maintain that X is almost uniform. So what we actually want is that X is almost uniform. Really what I mean by this is just a random, like, so I think of R as equal to X times Y, right? And if I look at the uniform distribution over X, this is my capital X here. Then I want that this distribution is almost uniform in a very strong sense. I'll like quantify it in a second. And I want to say that Y is large. And like somehow intuitively, I hope this is clear that if we have these two properties, and X is really good enough uniform and Y is large enough, then we should still be able to kind of maintain this kind of thing because we are so lossy in this step eventually. And we can grant ourselves some loss in this almost uniformity, just being large instead. Okay, let me make this formal. So first I have to tell you what the mean entropy is. So let me just write down, or no, let me, yeah. So the mean entropy of distribution is the bits required to write write down the most likely probability. The most likely probability in the distribution. Okay. Yeah. So let me just define by symbols. So of a random variable x, the mean entropy is simply the minimum of the logarithm of the inverse probability for x. Okay. So let me I don't know whether you have all seen this before. So let's just see. So if x is uniformly at random from 0, 1 to the k, what is the mean entropy of this variable? So you have to look at what is the largest probability any outcome will take, which is 1/2 to the k. And then we look at how many bits required to write this down, and this is k. Okay, so if we look at this variable, then we have the mean entropy of x is equal to k, and this is also the maximum in that sense, right? And if I have the very stupid probability that x is just equal to a fixed string, what is then its mean entropy? Zero, yes, because, well, probability is 1 and I require nothing to write. Okay. And then, yeah, I mean, yeah. So if I have a bit of more interesting probability distribution that takes maybe some value 1/4, 1/2, 1/8, and 1/8 probability, mean entropy is.
Just plug it there.
Yeah, I'm not doing it for myself.
One interesting thing here is to compare the entropy and the min entropy, right? I mean, so suppose your distribution is fixed, the all zero string with probability 1/2, and otherwise sample completely at random with probability. Then, like, the entropy of this is great, but the min entropy will be terrible because the all zero string is very heavy. And we read, so it's kind of a worst case entropy, if you will, which is, I think we'll see a little bit later. So this is the second way of doing lifting. The way we did lifting, we built this graph and we talked about the min degrees. So I think this is sort of will play the role of min degree if you're doing graph-based lifting. So we'll see the details later. Just sort of trying to make people help them to contrast and compare. These are two different approaches to lifting, and so it's great we're seeing both.
All right. So this is mean entropy. Yeah, it's a notion, and will we obtain like somehow this notion of x almost being uniform will have to do with mean entropy. In particular, we'll enforce that x has mean entropy, but we'll enforce even more, namely that any marginal of x also has large mean entropy. Okay. Let me write this down. So a random variable so let me write x in n the j. Okay, so j is a subset of n, say, because this is what we look at. Then it has is delta dense random variable x is delta tens if any marginal, so if for any set I, non-empty, I guess, contained in J, it holds that the min entropy of the marginal of x on J is delta times the maximum, which is the maximum is just size of I times log. Okay, so we want that the min entropy of the marginal of x on the set I, right, is at least delta times the maximum. What is the maximum? The maximum is just size of I times log. Okay. So this is telling us that this random variable is not just close to the uniform distribution, but even every marginal is very close to uniform. Right? How could you, like, think of having one coordinate that is fixed. If you fix one coordinate, you're not going to drop the min entropy of the whole random variable by much. It's very little that you lose. But somehow this is telling me that no, not even that happens. Like even if you look at a single variable, like a single subset, like singleton, you still have large min entropy. So this is like our measure of saying that a random variable is very close to uniform. Okay.
And you were shooting for delta, we should think of as very close to 1?
0.9.
0.
Yeah,
It's not too close.
Yeah,
but
it should be
fairly
close.
Yeah. Maybe I got lost somewhere. Where is this randomness coming from? So I thought you picked up.
Yeah, very good. And we look at rectangles.
Yeah.
And these are defined by some set x and some set y.
Yeah.
And I will look at the random variable over the set x.
Uniformly chosen.
Yeah.
Uniformly chosen. Yes. Uniformly chosen over x.
Mm-hmm.
And then I'm interested in the marginal.
Mm-hmm.
Right? X is going to be m to the n.
Yeah.
And so I want to say that on every marginal we have a high n.
But what about the y? How do you pick the y?
Yeah, relax.
Okay. Okay. So you're just picking x randomly.
I'm just
Almost
picking x randomly,
Okay.
and this is my notion of, this is our what we want to maintain on the x side. On the y side, we're just going to maintain that y is large.
Okay.
I'm not going to pick y. This randomness argument is just as a notion, as a something that we can maintain. Nice invariant.
Okay.
All right. So then with this notion of delta tens, as I already said now, I don't know how often, so we can now define the row structure. We can say a rectangle R equals x times y is row structure if the following is satisfied. One, we want that the random variable x restricted to the domain of the row is fixed. What am I saying here? Here I'm saying that if we look at the random variable x and we look at the variables that are assigned by row, okay? Think of row as a partial assignment, and then I look at the marginal on the domain of row, so everything that row actually assigns. Then I want to say, well, this is just constant, nothing is happening there. Okay, so all the x's agree on the domain of row. Okay. And furthermore, I even want that the y string is well behaved with respect to the fixing of x, so that this thing here is satisfied, that everything is completely. Because you could flip the y strings so that you get the wrong things. Wow. Fixed and every z in the image of G of R, we have that it is contained in this conjunction of a consistent way. Okay? So what am I saying? I'm saying that on the x side, which is like the pointers from Alice, we fix the pointers always. And then I'm saying that if we look at what we actually get as an output, this means like the Y string, right? So what am I saying? Like we have our pointer into this long Y string. And this one is fixed by this first property. And then I also want that the bit here that we find is actually consistent with rho. Okay. This is property one. This is somehow just a sanity check. Like this one is not very interesting in the sense that this will be automatically satisfied. Two, we want to maintain that x on the other variables, so x on, how do I write this? I guess rho inverse of star is 0.9 lengths. And the third is that y is large. Y is large. So what are we saying? We can also write it in terms of mean entropy. So mean entropy over y is larger than mn minus n cubed. But really what you should think of what we're saying here is that the size of y is just exponential. Okay. So this is what it means to be rho structured. All right. And this is the property that we'll be able to maintain during our walk down this DAG-like proof. Okay. And yeah, what I tried to explain before is that if we are actually rho structured, then we're also rho-like. Okay. Why is this so? Because if x is almost uniform and y is very large, you kind of get all the assignments. You're not just containing them. Right? So I guess I'll erase the theorem. So what is our lemma? So this is lemma. We will not prove this today. This is saying if x plus y is rho structured, then x plus y is rho-like. Okay. And furthermore, there's actually a single row that is rho-like, a single row that is rho-like. And there is a single row x, so there's an x in x, so that x times y is rho-like. Okay. Yeah, so this first thing here that x times y is rho-like is kind of like an averaging argument, and then you get this basically for free. That's what we have now, why you can get this for them. Okay. All right. So we have our invariants that will maintain walking down the proof, and we can show that then it's rho-like. So we can somehow relate whatever we're walking down that is rho structured with the left side, and we can somehow build a proof out of this by like looking at this row. Okay. Still not quite where we want to be. But if we are looking at our proof, right, and we are at one step, we get a rectangle. We don't know whether this rectangle will actually be rho structured. So somehow the final ingredient that we need is to say that give me any rectangle and I find you some rho structured rectangles in there. Okay. So this is the second lemma that we'll also not prove, which is the partition scheme lemma. Okay. And which basically tells you that you can take any rectangle and you can break it up in a smart way so that most of it will be covered by rho structured rectangles. And then you have some error rows, which we just remove. All right. So what do we have? We're given a rectangle. And now I'll tell you a procedure which will break it into pieces. And then I'm claiming that most of them will be row structured, except some small errors and columns. Okay. And what will this procedure be? Well, it will consist of 2 rounds. And in round 1, we'll basically just look at every maximal set that violates density. Okay, denseness. Okay. So if you find any subset which has too low mean entropy, then you take those rows that certify this, you remove them from the rectangle, and then you repeat. Okay. So what do we do? So in round 1, and so we said let I sub I containing n be such that the random variable on this marginal has low mean entropy, be such that a maximal, so it's a maximal set, be maximal such that I guess the mean entropy on x sub I is less than something like 0.95 the maximum. Size of I sub I times log m. Okay, so if it's like 5% off the maximum mean entropy, then we say, oh no, this is bad. We let alpha I in, I guess, n to the I sub I witness this. So this is like the 2 likely outcome, right? And then we let the set xi be all the set x's that agree with alpha I. Okay, so these are all x's, so that x sub I sub I is equal to alpha. Okay, and then I update x to be x. X becomes x minus x sub I, and we repeat. Okay, so what happens? Let me repeat. So we find a subset on which we are not dense, right? Which witnesses this, which means that the mean entropy is large. Having large mean entropy means that some probability of some outcome is too likely. Fix this to be alpha, and then remove all x's that agree with this alpha from your rectangle. And then repeat. Okay, until either your rectangle is empty, or I mean, if I sub I is ever empty, the empty set, that's also okay, which means just everything is fine, and we're done. Okay, so what happens? We like chop this into pieces, and now in the second step we're going to chop it with respect to y. Okay, and what it will do, it's nothing interesting in the sense that we look at a set I sub I, and we want to be fixed on them. Okay, so we pick all the y's so that I sub, like the assignment to I sub I, like a row, so to say, the unlifted world is fixed. Okay, so round 2. So for every x sub I, we're going to chop it now into blocks here. Okay, and these are going to be called something like y super I, comma gamma, where gamma is going to be the assignment that get that lifted. So for each, I think x sub I, and every gamma in 0, 1 to the I sub I, we define the set y sub I gamma to just be all the strings y, so that g of alpha I y I equal to gamma. Sorry, this is a bit messy. But what I'm saying is that we pick all the strings y so that if we look at whatever is consistent with x, which is alpha on I, right, on the capital index at I, and with y, then we get gamma. So we just want to be fixed on I, on capital I in the unlifted world. Okay, and this defines us this. Okay, good. And then we output all the rectangles, right? So finally we output all the rectangles R super I gamma So x I times y I. And I guess this here should be non-empty. Whatever, I don't know. Okay. Yeah. So once again, we on the x side we pick subsets that witness that we're not 0.9 dense. We chop it up by this, and then on the y side we just fix basically the string that we want on this subset. Okay. So far so good.
How did you end round one? What's the
We
termination
We
criteria?
end once the x set is empty. Like this means basically that once I sub I is the empty set. Like once you cannot witness anything that is ill-behaved.
Yes,
Right.
the minimum should be large enough.
What?
Once the minimum.
Yes, exactly. Yes. But no, if it's actually 0.9 dense, right? Not just the min entropy, but any subset of it has limit.
I guess what I don't see in round one, it seems that once xi is empty, then you're gonna cycle forever.
No, I said already without writing it down that we stop once we're empty. I have not written it down. Until x, y, I guess, y, x, okay. As long as x contains something, repeat. Every time x shrinks.
That is why there's not empty.
Why? I mean, if you don't find an I sub I.
And you have some I sub I.
No, if I sub I,
X is not dense. Like if X is dense, then you also don't want.
but I sub I may be empty, right?
Yeah, then what happened?
Then everything is consistent with that. Alpha I will be that partial assignment that doesn't do anything.
Okay.
Then x sub I will be x.
Okay.
And then we'll have empty.
Okay.
I think it's fine.
But then you will stay in the while.
No, because then x is empty. Let me say again. If everything is 0.9 dense, then I sub I will be the empty set because it's a maximal subset so that this is satisfied, right? So it's empty, which means that alpha I is the empty assignment. Everything is consistent with the empty assignment, which means that x will be the empty set after such a run. Okay. Good. So yeah, so we chop it out. These rectangles, I guess. Okay. And now we'll have to prove some property about this. And basically what we'll say is that either such a rectangle is actually row structured. So just as a sanity check, any such R satisfies the first property, right? This is how we chose it. Like we fixed gamma so that the output will be gamma on this set I sub I. Okay, we're fixed on that. Okay. The second part that it's 0.9 dense is because we chose x to be maximal. So if you would have something that is still violating density, then you could have added it to the maximality, like to this maximally large set. So you're done. That's kind of the intuition. And then that y is large, you need to argue, but it's not large. Okay. So what we want to say is that either this rectangle is actually row structure for a small row, okay? Or the rectangle is covered by one of the error rows or the error columns. So we'll have some error rows, x sub error and y sub error. And any rectangle completely covered by it will give up on, okay? So the things that are shaded red, those rectangles are actually covered by the x and the error columns, right? And on those we give up. And the rest we're going to say, well, the rest here will be row structured with a small row. Okay. Very good. Okay. So let me write this down. So, yeah. What I forgot to mention that we want this X error and Y error to be small so that we can remove them from everywhere in our group. So that this should be a small fraction. Right. Let me erase the entries. So lemma. So we can fix any k to be at most n log n. And what we'll actually fix it in the proof, just to like, this will be, k will be chosen to be 2d log n. Okay. So we're given a rectangle R, and let us say that it will be decomposed disjointly into these rectangles R sub I by this procedure. Okay. Then there are error sets X sub error, Y sub error of density at most 2 to the minus k. So what I mean by this is that the rows of X error will be at most a 2 to the minus k fraction of the entire rectangle X. Okay. This is what I mean by density at most 2 to the minus k. Such that either a rectangle Ri, either Ri is row structured with the domain of row being bounded by something like k over log n, or otherwise Ri is covered by the error columns or error calls or groups. Okay. So as in this picture, either a rectangle is entirely covered by either the X error set or the Y error set. These are the ones that I shaded red here, or it is not. And if it is not, then it really is row structured with a small row, which has like the domain of row is going to be k over log n, which for our choice later on will be just 2d. Okay. And somehow this link, right? Because we know that row structured things are actually row-like, and because row is going to be very small, we know that we can somehow extract a small subcube of width at most d. Okay. And then we also need an alignment property, which is a bit annoying, but let me just. So furthermore, we have that for every x in m to the n minus the error set, it holds that there is a subset I sub x contained in n. So there is again of size and most k over log n. So the size of I sub x most k over log n, such that every structured Ri intersecting this row has its fixed part within this special I sub x set. How do I write this? Such that every structured R sub I intersecting row X and satisfies that the domain of row is actually contained in this I sub X. Okay, so what is this saying? Look at any fixed row, and look for every fixed row that we look at. So look at a fixed row here. Then I'm saying that for this row X here, there exists a subset I sub X contained in N, so that any structured rectangle that intersects this row satisfies that its fixed part is contained in I sub X. So the domain of row, where right the row comes from this row like, I guess maybe row sub I is a bit better. That is domain of row sub I is contained in I sub X. And this should be pretty clear, like from this construction here, because we just, well, yeah, if you intersect the row, this means that we need to satisfy this. Okay, so the I sub X will just be the domain, but it will be important later on. All right. How tired are you?
I mean, the suspense is getting enormous, no?
Yeah, so now we have actually built up all our tools. So, I mean, yeah, so these two lemmas I will not prove today, but we are actually now in a position to do the proof module these two lemmas. And it will be somewhat disappointing because nothing will be happening, and it will be somehow everything ugly will be hidden in these two lemmas. Or ugly, I don't know. All the work that you need to do is actually hidden between these two lemmas. Okay. All right. Okay, so what do we do? So first, for what follows, we will just ignore the error part. Ignore for now. Okay, let us just ignore this. I don't want to talk about it. Okay, we can talk about it later if there is still interest, or otherwise on Friday. Okay, what will we do? So as I said before, we're going to walk down the given DAG, right? We're given a rectangle DAG pi of size n to the d, and we'll want to construct a resolution proof of width d. Okay, fine. And what we're going to maintain, right, at every node here, we are associated with some rectangle R. We're going to maintain an R prime contained in R, such that R prime is row structured. Okay, that's all we'll do. Very good. Questions? I'm serious. Like,
So
now we need to check
again, R is the rectangle defined by this.
At this node, we have some rectangle, which is defined by our DAG. Our DAG is labeled by rectangles. We have this rectangle there. We're going to maintain some row structured rectangle.
So a cleaned up subrectangle.
A cleaned up subrectangle. This is all. This is what we'll do. Okay. What does this mean? This means that we're going to have our in the right. So this is the lifted world. In the unlifted world, we're going to be actually like playing a prover defendant game in a proof, right? And our state is going to be row. Okay. So keep this in mind. We have the lifted world where we have the rectangle R. We're going to maintain a subrectangle R prime, which is row structured. And on the unlifted world, what we actually want to construct, our low width resolution proof, we're going to maintain row. This is what it will maintain. This will be our game state. All right, very good. We need to check three things. First,
we identify the partial assignment row is just identified with the largest possible clause that is falsified by row. This is this duality that I think of partial truth value assignments as falsified clause.
Yes, exactly. Okay, very good. We need to check three things. We need to first check at the root that this makes sense, namely that when we start the game over here, row better be empty, right? You cannot just start with an arbitrary assignment. So this means that at the root, we also want to say that R prime is start to the end structure, right? Or like where we start in the beginning. That's the first thing we need to check. The second thing we need to check is that whenever we do a step, which is the most interesting thing, that we can actually go to another row structured rectangle in low width. And then finally, we need to check that in a leaf, we actually have a solution, that we are actually, right, that we end up in a solution. All right, we'll do them in order. So one, the root.
Having a bit of control of the size of row would be nice also, but that's given by the lemmas already.
Yeah, right here. So I said that we're going to choose k to be 2D log n, which means that our row, the domain of row is going to be bounded by 2D. Okay, so then we have taken care of. Good. Okay, the root. So at the root, what I want to say is that if I apply this procedure to the entire rectangle, then it will just return me the entire rectangle. Okay? Because if I have the entire rectangle, this means that it's star to the end structure and we have a valid beginning. Okay? So we claim that the partition procedure outputs the rectangle R, which is equal to m to the n times 0, 1 to the m to the n. Okay. Are there questions why this is the case? Should be clear. And so therefore we actually start with a rectangle then with row empty. Okay, so we can actually start again. All right. Most interesting case is how we walk from a node to one of its children. Okay. So at this node, we have some rectangle, and we have the subrectangle, which is row structure, right? Which we actually maintain. So actually, I want to forget about its original rectangle and just look at the subrectangle, which is structured. Okay. So this here is going to be my R prime. And I know that my two children are associated with some other rectangles. So this is, let's call them L0 and L1, which cover R prime. This is like the property of DAG-like protocols. This is exactly what it will be. All right. So then what do we further know? So this is row structured. So in particular, we know that there is a single row so that x times y is row-like. Let's call this x star. Okay. In particular, we know that because we are row-like, this means that we can obtain all assignments consistent with the row, right? So in particular, there is going to be one assignment y star that is consistent with row. Okay.
They all should be, and you're just picking one? Or
well, I just want to have, right, I know that x star is row-like, like the row is row-like.
Mhm.
Are we using the first lemma, the second line?
Yeah, that's clear. I'm curious. I don't understand how we're choosing this Y star.
Okay. Sorry. Yeah. Sorry. Asking for this. Sorry. Okay, fine. So we have the row X star. You agree on this? It's row like. Sorry.
Are you using the second line of the middle board lemma now?
Yes.
Okay.
Okay.
Because it's structured so there's like Alice sort of has a single
Yes.
vector which actually could support anything on both sides.
And we know that if you look at the partition of L0, like this partitioning of L0, then any rectangle that intersects the row X star has this property that its domain of its row I is contained in some set I sub X, which is small. Okay, so right, this set I sub X is small, which I would assert. It's again of size 2D. Okay, and this is true for both, for L0 as well as L1. So I can query this, right? So we know that any L0 super I, or let's just write LB I rectangle intersecting row X star satisfies the fixed, right, the part that is fixed on here. So the right, this L sub super I sub P is associated with some row sub super I sub P, I guess. Okay, because it's row super I sub B structure. Okay. So and we know that we have the property that the domain of row super I sub B is contained in this set I sub super X star sub B. Okay. So there exists this set, this small set, so that this holds for all such rectangles that intersect row X star. So there exists this set I B X star such that any LIB rectangle from the partition of Li, right, that actually intersects row X star satisfies that the domain of its fixed part is contained in this small set. So what I'll do first is I'll query everything in here from B0 as well as B1. Okay, I can do this. So far so good. Right, on this side. So this means that my assignment now tripled almost inside, right? So now my size will be like 6 times d. The width will be 6 times d. Okay. And now I can use the fact that X star is this line here is row-like. Like, right? So this will give me some, this will give me some row stars. Okay. And the domain of row star is much more than the row we started with. Right? We started with row here. But now I know that this row here is a row structure. But because I know that it's row-like, this row is row-like, I know that there is a Y star that is consistent with row star. Okay? So I find here a Y star, at least one, that is consistent with row star. Okay? Now I look at, well, what rectangle does this lie in? I go to this rectangle. Then I forget everything that is not in the fixed for this rectangle. Okay? This is all we do. So let me repeat. What do? We start with a row structured rectangle, which is a subrectangle of what we actually have. We look at the two children L0 and L1. We look at the row, which is actually row-like. Okay? And then we know that this row, if it intersects with any rectangle in L0 or L1, right here, intersects with all these rectangles, then I know that these have all the property that somehow the domain of the row associated with this rectangle is contained in this small set I. So I can query these two sets. I'll increase my width, I'll triple my width, but that's fine. I get row star. I know that here I was row-like on this row, which means that I can find an y star, such an x, y star is consistent with row star. I find this one point, or probably even several of these points. I go down into the rectangle beneath, the structured rectangle of the child, and I'm.
And there is such a rectangle in one of the child, potentially in both, maybe, but then you just, take your pick.
Yes.
But you're gonna walk down left or right.
Yes. This is the proof modulo the leaf case. We need to argue that we actually, the leaf will actually falsify an axiom. And for
Where
this,
do we,
there's
I mean,
not
the
use
row blow up terribly. Where are we shrinking it again?
No. It's tripled, and then we went to this rectangle,
Yeah,
and we forgot everything except the domain of this rectangle.
right.
And then we're down back to D.
So we're down to like size of this,
2D.
is this IX thingy or?
We're down to the size of this K over log n, and K is 2D over log n. So we're back to size 2D. Okay. We also need to check the axiom. Nothing's happening there. Yeah, let me just. So the third thing we need to check is the leaf case. And here, what do we have? So we have row, which is like the row that we have, and we have R prime, which is row structured. So we know that we're labeled with some O. So we know that R prime is contained in S composed with G inverse of O. But this implies that G of R prime is contained in S inverse of O. We know that this here is equal to C inverse of sub row of 1, which is showing that C inverse sub row of 1 is contained in S inverse of O. So the output is correct. Where for this step here, I once again use that we are row-like. So the definition of row-like was that this is equal. Like this is really like the leaf case is just the whole thing is set up so that this works. There's nothing. Okay. I mean, to me, this is very underwhelming when you see this proof. Like you set up these elaborate, invariants, right? And then you're just like, yeah, now it works. Let's move on. But somehow we did, it's very unclear where this is coming from and why this is the correct thing. So I think it's interesting to actually understand why these properties are the things that. Okay. I haven't told you what to do with error sets. The 3-second explanation is you traverse the DAG in a topological bottom-up manner, and you remove the error sets one by one, and you output the rectangles that you have, and everything. Like you process this to the root. You know that by our choice of parameters, the density of these error sets are very small. It's very little, so we're basically left with the whole thing, and we can just ignore it, put it under the rug.
But actually, the fact that the root covers everything now is non-trivial in the sense that you want to check that I didn't remove so many errors that somehow I don't have anything at the
Exactly. But the parameters.
But if I have this, then I'm good to go.
Yes.
With the rest of the
Then
proof. So the
everything-
error sets are only like that's a pre-processing space.
Yes. You do it in pre-processing, and then you can repeat this. Okay. I don't want to say more. I feel like I've gone already way over time. So my plan for Friday, unless there is serious objection, is to cover these two lemmas. I still haven't decided on what proof I want to cover, but I have to figure this out. This is my problem. So either it will be based on sunflowers or it will be information theoretic or like, yeah. Yeah. I'll decide. This is it from me. Hope you enjoyed it.
We have to do the sunflowers.
I'm not sure. So the problem,
What was the question?
whether sunflowers or the Fourier analytic proof, which one to do. So the problem with the sunflowers is to me that I don't understand it in a sense. I can tell you the proof and you can verify that it's correct. And we'll convince ourselves that it's correct. I'll not be able to give you any like idea of what's happening. The other proof I haven't read it in detail, but when I read it, it was like, oh yeah, these kind of statements make sense. I understand what's happening. That's why I'm not.
Excuse for you to understand it.
I guess. I don't know. So yeah, I don't know. So this is why I'm a bit torn.
But somehow we're hiding the complicated. Yeah, this, as you already said, sort of all of the interesting stuff goes into the lemmas, right? Because if you view this as a simulation argument, you can. One thing we really want to keep control over is that rho doesn't blow up in size. Like we're really, because if you're a prosecutor, you want to keep your rho small. And so somehow there's some budgeting procedure where rho, I guess, is never larger than, you know that you're starting with a DAG of size like n to the d, and now you know that, okay, my rho budget is d log n. So whenever actually, like somewhere there's going to be like a, the crunch time when you need to argue that.
This lemma is not so hard. This is quite immediate, surprisingly. Like showing the limit on the size of your rho is not the hard part. The hard part is this lemma, the full range lemma. But here you're not talking about the size. And like the size of rho is almost immediate from this procedure.
Yeah, but it stands to reason the smaller rho will be, the harder the full range lemma will be, right? So.
Yeah, I suppose. Yeah, we'll see. Yeah, as I said, I haven't read it in detail. So it's fascinating. False. Stop the recording.